So the next thing that I want to talk about is that you can take unions and intersections of more than two sets. And this is not too much harder, but it's worth saying something about. Can be, as always, when you start taking more things, it can get a little bit more subtle. So for any collection of sets, A1, A2, up to AN, we define their union to be, we have this, so you can write A1 union A2 up to AN. You can also write, there is this slightly more convenient notation, which is just a big union from I equals 1 to n of AI. So if you've seen summation notation before, it should remind you of that, right? This is basically denoting some set that our operation is spinning through, and then these are the things that we're applying it to as we spin through that set. And of course, maybe you can guess what this is, but let's write it down. This is elements such that X is an element of AI for some I. So if I wanted to say this in another way, I would say that there exists an I such that X is an element of AI. So at least one, right? And intersection is likewise a big intersection sign, and it is elements that are contained in these sets for all I. So again, it's union operates like an or, and intersection operates like an and. And we can even, where it starts to get, even more subtle, even for infinitely many sets. If you have an infinite collection of sets, you can still define these things, and you write union from I equals 0 to infinity, or intersection equals 0 to infinity. Again, the same way that you would with summation notation, if you've seen that before. So let's draw some Venn diagrams just for good measure. So this is A, B, and C. And let's shade A union B, union C. So what is that? That is just this whole area. Everything that's covered by any one of these circles. There we go, that's the union. And then the intersection. That is going to be the place where all three of them overlap. So it doesn't include places where two but not three of them overlap, of course. It's only this area where all three of them are. So again, some concrete examples. So let's consider the real numbers again. And we can write this as an intersection of real numbers that are at most -1 and real numbers that are between -2 and 2. And I think I want to move this over so I have space right there. Union real numbers such that they are at least 1. So let's draw a picture of this. This is saying that if we take the real line, which looks like a line, there we go, 0, 1, 2, and -1 and -2, then, so this first set is things that are at most -1, so it's like that. The second set is things between -2 and 2, so it is like this. And the third set is things that are at least 1, so it looks like this. And to say that it's the union of these 3 sets is to say that every point lies in at least one of them. And you can see that it does, right? These points all lie in this set, and then these ones lie in this set, and then these ones lie in this set. On the other hand, if we take the intersection of these 3 sets, let me not write it again, but so that is the elements that are in all 3 sets, and that is the empty set. Because although you can see that these 2 intersect here and these 2 intersect here, there's no place where all 3 of them intersect at the same time. So the 3-way intersection there is empty. Another example. Here's an infinite union and intersection. So if I list P1, P2, the list of prime numbers, then, and I take the union, for each I take the set pi times n, and in integers, then I'm saying that I can make all the integers this way. And this is indeed what is written in my notes, but I'm realizing that I actually missed something. So let's modify this a little bit, because there are just a couple of numbers that are not divisible by any prime, and those are plus and minus 1. So if I take the union over all primes of the numbers divisible by that prime, I get all integers except plus minus 1. And then if I throw those 2 in as well, I get all integers. And on the other hand, what happens if I intersect all these sets? Which is to say, what numbers are divisible by every prime? There is one of those, and maybe you can guess what it is. It is 0. So 0 is the only number that is divisible by every prime. So as like a quasi-application kind of thing, I just want to make a little connection that union should remind you of proof by cases. For example, our proof that the absolute value of xy equals absolute value of x times absolute value of y, which we did sometime last week. Essentially, this uses the fact that the real numbers, or yeah, not real numbers, but we were considering pairs of real numbers, right? So if we consider all pairs of real numbers, we can split this up into those where they are both greater than or equal to 0, or x greater than or equal to 0 and y less than 0, or x less than 0, y greater than or equal to 0, or both less than 0. And okay. Just to be, clear about what I'm writing, I'm using a little bit of informal notation here. So I'm not, this is not, a full step builder notation or anything. I'm just writing this to be understood as subsets of these satisfying some conditions. So remember this proof, we broke it up into 4 stages, and we claimed that proving it in those 4 cases proved it in general. And that's essentially saying that these 4 subsets union to this big set. And for intersection, there is also an analogy there, although it's not something that we've given a name to. But for example, if there was something that you wanted to prove, if there is some number that you wanted to prove was 0, and you proved that it was divisible by every prime number, then you can conclude that it is 0, essentially by this fact, that if it's divisible by every prime number, it must be 0. It's essentially saying something about an intersection.